But so I'm hoping to do is finish chapter 3. I might start chapter 4. If not, then we'll see. We'll see how it goes. Okay, I'm gonna get started. Okay. The homework is due. I think it's due tonight, if I remember correctly. It's on Lumen Learning, so just look there. All right. Okay, so last time in chapter 3, we looked at linear functions. And if you remember, a linear function, that's just a function whose graph is a non-vertical straight line, okay? And again, it's just a function whose graph, excuse me, is a non-vertical straight line. So, so in other words, it's going to look something like this. F of x equals mx plus b, where m is the rate of change, and b, of course, is just f of 0. In other words, that's the initial value. It's what you get when x is 0. In general, if you have a vertical straight line, that's not going to be the graph of a function. There is something called a vertical line test. I've done it in Math 104. The book I don't think does it, so I'm going to skip over it. But basically, a vertical line is not the graph of a function, mostly because it can't. Well, let me not go there. Anyway, so, and also again, remember your m here. It is the rate of change, which again basically means if you increase x by 1 unit, then your function, your y values, your output will change by m units. That's what the m is. M is the rate of change of the function. It's also called the slope for a linear function. Okay. I mean, I did show last time other ways of writing an equation for a straight line. You had y minus c equals m times x minus a. I think it was something like that. The mx plus b is really all you need. So I would just stick with that. So that's what we have. Again, it's called the slope. So slope, rate of change, same thing. So again, this is just some stuff that we did last time. And this is actually how you can calculate the rate of change or the slope. Again, you could just take 2 different points, as you can see. You subtract their y values and divide by the corresponding difference in x values. So you subtract the y values divided by the corresponding difference in x values. Again, the rate of change is the slope. So it's the same thing. So, again, you could just take 2 different x values that are not equal to, well, they're different, calculate the corresponding y's, and then use this formula. So the picture there I'm showing, that's just really to help try and illustrate the rate of change, what it does. So in other words, if you increase x by 1 unit, your output, vertical change, that's going to be m units. That's all I'm trying to show there. You might have seen that, I think, when they first introduced the slope of a line. I think they might call it rise over run, but but either way, this is what we have. Okay. This is what we have over here, that kind of thing. All right. So we have that. Okay, so let me just get it. Let's dive in and do another example. We did some examples last time, but I think it's good to do some more. So for instance, here, right, we have f of x is 2x plus 3. And basically, I want you just to confirm the rate of change is 2. Another way of saying that is, I just want you to calculate the slope. And the slope you should get is 2. So let's just do that. So essentially what I'm doing here is I'm taking x to be 0 we calculate f of 0, and we get a point, right? Now for 0, you really don't have to do this, but I chose 0 just because I thought it was the easiest. But you can really choose any number you want. You could choose 1, 3, -5. You could choose 1,000,000,000 if you want. Why would you choose 1,000,000,000? I don't know, but you could do that if you really want to. We also have here 1. So we have 1 as well. Okay, so, and again, I just chose 1 kind of randomly. Next to 0, it's an easy number. Easiest number, I guess. Calculate the output, right? And from each input and output, we get these points, as you can see. And then we just calculate slope. That's all. See? Change in output over corresponding change in input. 5 minus 3 over 1 minus 0. Change in output over corresponding change in input. Doing so, we get 2. So, no surprise, because you can see from here that since it's in mx plus b, the coefficient of x is m, which is our slope. So no change there. And I also said confirm the rate of change was 2, so no surprise that we should get 2 there. So, and really to drive it home as well, I also graphed it. I used actually what they call GeoGebra. I think it's on the computers on campus, but if you're not on campus, you don't have to download it, but you could. It's a free thing to use. And again, all I did here was I graphed the line. And the triangle here, I'm just trying to illustrate this rate of change thing. If I increase x from 0 to 1, if I increase x from 0 to 1, the corresponding change in your output will be 2 units. In other words, y will increase by 2. And that's what's happening here. It starts out at 3, but then it's going to rise up to 5. So that's all I'm trying to illustrate here. I really do hope it makes sense. Okay. So that's what's happening here. All right. So that's one example. And the notes I did post on Blackboard, if I remember correctly. I hope I did. But either way, I'll definitely post them later as well. And this is just something that will come up when we do some word problems today. Basically here, what we're going to have is units for slope. Excuse me, the units for slope, also the units for rate of change. You could probably guess from the formula, it's going to be units of output over units for input. Generally in a word problem, if you see something like that, you have some kind of unit, then per, PER, then another unit, like dollars per minute or miles per hour, right? That's usually going to indicate there's some kind of rate of change there. That's going to indicate there's some kind of rate of change there. So that's what's happening here. But anyway, here's another example I want to do. So this one's not really an intense word problem. Excuse me, it's not really an intense word problem though, but I thought it would be good to do. It's basically asking you to interpret something. So I give you this function v of x, which by definition is this. And here I'm just telling you that this is the value in thousands of dollars of some investment after X years. What is that investment? We don't know, but for now it doesn't matter. But notice the units are thousands of dollars. So what would V of 10 be, for instance? Okay, well, we can calculate it directly. That's easy since we have a formula, right? You just replace X by 10. As you can see, we replace X here by 10. And we get negative 19.8 thousands of dollars, which is the same as saying negative $19,800. Negative $19,800. Same thing. Same thing. Okay? So now that's what V of 10 is numerically. But what's the meaning of that, though? Well, that's where the definition of the function comes in. That is this stuff over here. This is basically telling us in words that 10 years after, no, excuse me, the value of an investment 10 years later, it will be worth negative $19,800. In other words, it's going to lose in value $19,800. So yet another way of saying it, the value has decreased by $19,800. Okay, so that's what happens here. All right. So that's the meaning of it. Okay. So it's not just numerical, it's also what the meaning we're looking at. Okay. And what would the rate of change be? Well, the rate of change, well, that is actually given to us, right? That's what the coefficient of x is, which is negative 5.4. In other words, the rate of change, it's negative 5.4 thousands of dollars per year. And so again, what does that mean? That means the investment is decreasing in value at a rate of 5.4 thousands of dollars per year. So basically by the problem, it's starting out, this is the initial value, which is 34.2, and every year it's decreasing at a rate of 5.4, which in the context of the problem is 5.4 thousands of dollars per year. So, yeah. All right, let me just, I got to stop because, well, not with the lecture, but what the heck? Okay.